Hi everyone, in this video we are going to be covering about the LSM tree. So before starting with LSM tree, we need to first understand the basic data structure, that is SSTable, which is the backbone of LSM tree. So we'll start with that. So for SSTable, what we want to understand here is how the data is stored in an SSTable. So SSTable basically is a sorted string table. So I'll just write it down. It is a sorted string table. How the data is kept in SSTable is such a way that you have a sequential. So the important keyword here is sequential. So you have sequential data. Let's say you have key value pairs K1, V1, K2, V2, K3, V3, for example. So this is how the data is kept, and it is sorted. So it is sorted inside an index. Also, it is sorted on the disk as well when it is kept in this way. So let's say this is a file and it starts with 0 offset, and here is offset 100, here is offset 200, for example. So what happens is we also have a index. So the index contains two things. The index contains a key as well as offset. So the key can be something like K1 is at offset 0, K2 is at an offset 100, and K3 is at an offset of 200. Now these are sorted. So these are sorted. And the advantage, the main benefit we get from this being sorted is we can do really fast search. So we can do a log n search using binary search technique. So we can do binary search in order to find a key. So let's say we want to find K3, we first go to K2, and then since it is on the right half here, we find it. So we find K3, and quickly we can look up the offset, and offset we can directly access here. So it is 200 here, and on the disk we can quickly go over to this position and access it, right? I hope this makes sense. And this is what basically an SSTable is. It is used for quick lookups. So your random access is really slow on the disk. So what you want to do is a sequential access. So that's why the data is kept sorted, and we can do binary search also. That is one of the main advantage of keeping the data sorted inside your disk. Now we'll move on to the basic structure of your LSM tree. So we'll start with the basic structure. So the basic structure looks something like this. I'm not going to tell you like each and every component right now. I'll highlight a few components, and as we will start looking at the write flow, the read flow, the update flow, and delete flow basically, we will see how the LSM tree will form itself. So that I think is a better way to understand LSM tree, other than me completely like explaining you it beforehand and then telling you the flows, different read, write, update, all of those. So I'll start with few basic things that you need. So few basic thing that keywords basically you need are Memtable. So Memtable is basically your SSTable, but rather than it being stored on the disk, it is stored in memory. So when an SSTable is in memory, then we call it a Memtable basically. So if it is in RAM, we call it Memtable. Second thing that I would like to cover up is SSTable. So we have seen what SSTable is. So SSTable is basically just SSTable, which we talked about in this part, and it is, we call it SSTable when it is kept in disk, right? So the keyword is a bit different, terminology is a bit different. And there is another component called WAL wall. So it is known as write ahead log. So your write ahead log is basically just a append only file. So it is an append only file which keeps kind of a log of your operations, write operation. So if there is, let's say, a write operation that says write K1 to V1, something like this, then it logs it in some sort of a format that K1 is inserted or updated as V1, right? So it is keeping a log, it is keeping an audit kind of a thing. So it is an append only file. and it is in order. So basically, if you want to build up the database, you just need the write ahead log. You have your uh, write ahead log file, which will have some operations, operation 1, operation 2, and so on. And you can perform these operations in like reverse order. So you can also do compaction and all of that. But if we take a very naive case, the operation that was ran like with the largest timestamp or the largest time. So largest time by this I mean is uh, oldest time would be the correct way to. And in this order you can execute. So all the queries you can execute, and at last you will get a database that is in the state of whatever the data was before. If there is, let's say, a machine crashes and you have the write ahead log file, so you can rebuild the data quite easily. Right. So these are few things that we need to remember: Memtable, SSTable, and wall, write ahead log. And the other things we will cover as we go on deep inside the LSM tree. So now I think is a good time to understand the write flow. So we want to understand the write flow inside your LSM tree. Right. So I'll start with the structure, how the flow is going on. Let's say we have a user and it says write me K1 as V1. Right now I am just keeping it in such a way that there is no data at all in the database. And this is the first write call, right? What happens first? The first and the foremost thing that happens is this particular query or this particular request is written in some form to write ahead log file, as we talked about. So this is the first step. Write it to your write ahead log. This is done for durability purposes, for availability purposes. In case your machine crashes, you can easily build it, because we will see that we will keep a lot of data in memory, and in memory is never safe. Your machine can turn off, things can go out of control, you can have a out of memory error or something like that, right? So first step is write that request to a write ahead log. And the second thing that you want to do is write it in the your memtable. So inside your memtable you want to write this particular thing. So I'll write K1 as V1, and you'll also update the index, right? So this is your key and this is your offset. Since it is the first one, so I'll say K1 is updated with 0 offset. So I'll also mark it here. This is your 0 offset, right? So we have updated the data till now, and this is your write flow basically. Basically, this is how you write. You might have seen that like we are not writing to the disk actually. How is this even durable? How is this sustainable? Like your machine crashes, what happens? So for that we have write ahead log, if you can recall it, right? So this is your first step. You did a write request and you got the data, right? We will do a few more writes, but I'm not doing those writes actually. I'll just write them down. So let's say our memtable is in currently this form. So we have few data pieces: K1 V1, K2 V2, K3 V3, something like this, key value pairs, right? And I'll also write the offset 0, 100, 200. Also we would need an index, so I'll create an index here. So this will be our key, and the offset K1, K2 and K3, 0, 100 and 200, right? So this is how our memtable looks like right now. Now, before doing anything, I want to talk about the read flow. So I'll come back to how the data is being written to the disk. So it is not that everything can be kept in memory and you are in a happy state with your write ahead logs. That is not very sustainable, because building the database from scratch using a write ahead log can take a lot of time. And in case your machine crashes, you don't have that critical time, right? So you would also want to keep some data on the disk, keep some data on the memory, in memory. That's how you can achieve a good balance on like quick writes quick reads, all of those things. Right. So now I want to quickly cover the read flow. So read flow I'll quickly cover. One thing I'll do is I'll bring this particular piece of diagram below here. So we'll cover the read flow. Right. So we have the Memtable. Now let's say a user, for example, comes in and says, I want my K1 value back. Give me K1 value back. Right. How the flow will go now is you check it in the Memtable. So you have these as sorted. So these are sorted. You do a binary search. You find that K1 is at 0th offset. So here you can access it very easily. This offset. So 0th offset is, sorry, this one. Yeah. So I'll quickly go over here. 0 offset is actually this K1. And you can quickly give them the value back as V1. So this is a naive read flow when you got the data in the Memtable. I'll cover how you handle cases when you don't get the data directly in the Memtable because things are not that good that you directly get the data in the Memtable and you're happy. Right. Before that, I would cover the update and delete flow. And then I'll come back to the read flow where you don't get the data in your what I would say is Memtable, right? So I think we can quickly cover that as well, right? I'll just erase a few things from here, right? So we have our diagram, and I'll just cut it down just because I'm lazy. So I'll do the update flow now. So how the update flow works is also quite simple. You first go ahead and write in your write ahead log. Second is you update the Memtable and the index. This is what you want to update the Memtable and the index. The update is really easy. Delete. Delete is a bit interesting. So delete flow is something like this. So when you want to delete, you want to probably delete it from here, from your index as well. But the delete is not done that way. And you will understand it in like a few minutes that why delete is not simply removing. Why is it designed in such a way? So it is actually not a hard delete, not a hard delete, I would say. It is something known as tombstone. So something known as tombstone delete or a shallow delete, I would say. So a shallow delete is something, or soft delete also people call it by different names, right? Specifically, I will go with the name tombstone delete. So you don't actually delete the data, you mark the data as being deleted, right? So there's a difference between that. You don't delete the data, you mark some sort of a flag or something that this data is no longer valid, right? So delete flow is also quite simple. You come here, you of course write in your write ahead log that this data piece is deleted. Update the Memtable. So in the Memtable, what you would do is currently, let's say you have K1 here and you want to delete K1. You would change the value corresponding to the in the index. What you will do is for this K1, you will change the value. So here, rather than 0, you will have a special value. Let's say you have negative infinity or something like that. So offset can't be negative. So you can also keep -1 here. So -1 would indicate then that this data is deleted. So whenever you get an offset of minus or less than 0, you say that the data is deleted and it is no longer present, right? So that's how the delete flow works. Now we will cover the interesting part. The interesting part mainly is merging, compaction, how data is being stored in the disk, and then how all these flows are changed. We would understand that, right? So in order to understand that, first what we want to do is see when we are putting the data in the disk. That is important part. So what I would do quickly over here is I will bring back my Memtable. So this is my Memtable. I'll quickly draw it very quick. This is my Memtable K1 V1 K2 V2 and K3 V3. And what we have here is 0, 100, 200. This is our Memtable. This is our index. I'm not writing the header K1, K2, K3. And this you have now as 0, 100 and 200, right? So when is the data stored in the disk? So this can be configured. You can have a threshold. Let's say you have 1,000 entries in your index, or 1,000 entry here in your index or in the SS table. You want to flush it to a disk, which is like a totally valid way to do it. What you would do is just perform a flush operation, take everything that is in memory for the memtable and the memtable index and push it into the disk. So on the disk, it would look something like this. There would be a file created, let's say SSTable 1, something like this, and it will have this piece of data. So I'll quickly pick this data. So it will have this data, right? Sorry. Yeah. So what it would have is this and this piece of data. I'll copy it here and paste it. Right. So this is how the data looks in the disk as well. Right. So the data is kept on the disk in the similar way. And now what we want to do. So now your memtable is flushed, it is empty, and the data is in the disk. How now things changes. So when you are keeping the data in the disk, let's say there is a read request and you do not get the data in your memory, right? So what you would do is you would search your disk. You can't like search your disk like in a naive way, like you can't scan all the entries. You can do binary search here, which is a good idea. You can do a binary search. You can load the index in memory, load a file. So just load the index and then do a binary search. If it is present, it is good. If it's not present, what you would do is go search the second file. So basically what happens is when you have your, I would say this thing, your SS table, what you would do is there are a few smart techniques to make it very optimized. I'll talk about it. So I'll now go in the details about how an update works, how a delete works, all those flow when your system is in a different state, when you have flushed your data onto the disk. So now we will cover the update flow when the data is on the disk. So this is our disk and we have an SSTable01 file and the memtable is currently empty. We get a request to update K3 to V3. In this case, what we will simply do is we will update the wall first. So step one would be, step one is your update write head log, and step two would simply be update memtable. So inside the memtable, what we will do is we will say K3 new value is V3 dash, right? And now the question that you would have in your mind is why are we not updating it on the disk? So if you go back to the read flow, the read flow is something like this. You search the memtable. If you get the data, you return. So search the memtable first. If you get the data here, so if someone comes in tomorrow and says, give me the value of K3, you will find it in your memtable and you will return the value V3 dash. And this particular data is now of no use. So we do not want to load the data from the disk now and check in this case. So we can update directly in memory without changing it on the disk, which is really, really powerful and really quick, right? So this is one of the advantage of LSM tree that you would now start seeing. Next up, let's say we get a few more update events. Let's say we get update K1 to K1 V1 dash, something like this, right? I will make a state for this and then we will understand more topics like compaction and merging, how that happens. So this is another scenario that I will cover here. Let's say you get a read request for your value, something like K3, right? So now you would keep your files sorted as well. So you would read them in a certain order, in the order of the time that they were flushed on the disk. So the earliest one would be read first before the later one. So in this case, 2 is the earliest one and 1 is the later one. And if someone says give me the value of k3, so you would read it from here. So rather than reading it from randomly from any file, you would read it from the most latest flushed file, because here the value is v3 dash and here the value is v3. You do not want to read an outdated value. That's why you are reading it from in this particular order, right? And next we would want to see how we can remove this particular piece of data. So this data k3 value v3 is now of no use to us, and we would likely want to delete it, like remove it. So what happens in LSM tree is there is something known as compaction. So compaction, this is a process that runs time to time. And what is does is it would pick up like two files, like let's say it picks up these two files and merges the data. So there is a merge operation happening. What the merge operation does is if this particular value is present in the new file, keep that value. So k1 would be v1 dash and k2 would be v2 dash and k3 would be v3 dash, something like this. So discard the old values, keep the new values. If the value is not present in the newer table, keep the value that is already in the older table, because there is no update after that. That's why an older entry we have, right? So this is the compaction and merge. You can have leveled leveled compaction. You can have level compaction. I mean is, let's say you have some SSTable here, some SSTable here, and these are being currently used and level. There are more recent one. Then you have level 2 and then you have your level 3. Now, if you merge two tables, let's say you take two really old tables here and you merge them and do a compaction on them, they can go to level 2 now. Then they can go to the level 3. So the search kind of goes from level 1 to level 2 to level 3. And the compaction can happen in the background as a background process. The compaction might be happening, right? So I guess it makes sense. Also, one more thing that is very costly is, so this same thing of update applies to tombstone delete as well. So if there is a value being marked as deleted in your index, like -1 or something, you can do compaction on that as well, right? And what happens now is, so one thing that we can fairly easily optimize is, let's say there comes a request for K4 now. So we know that K4 isn't present in the database, in your data that you have built. But it is not very easy. You will first have to check the memtable. Checking memtable, I know, is very fast. It's in memory. Second, you would check the level 1 files of SSTable. Maybe you don't find it. Let's say you have 100 of file here or thousands of files here. Then at level 2, you have hundreds of file here. And at level 3, you have 20 files, something like this. You would have to search all of them to know if the key K4 is present or not, in case you do not have data for K4. And a pretty good optimization on this is your Bloom filters. So you can create a Bloom filter on the key just to tell if that key is present or not present in your database. So the Bloom filter gives you guarantee on not present, which is what we want. So it would say, oh, this key is not present. I am 100% confident on that. Or it would say maybe present. You can check it yourself. Maybe present. And the way you configure your Bloom filter, you can have some probability that only this many requests would have a maybe present, otherwise it would be not present or something like that. So you can have really, really good efficiency to check any value, and the memory footprint will also be very less in this case. It won't be a lot. So if you read about Bloom filters, you would know how it keeps the data. So if you would want me to make a video on Bloom filter, I can do that as well. So yeah, that's how we can quickly check if a value is present or maybe present or not present. So for us, not present is important, because if you do not get a not present, you do not use a Bloom filter, then you would have to go through all the files and the reads would be really, really slow, right? And also you can cache the data. You have your Memtable. If you have some frequently used records, you can cache it in the Memtable. You can do all those of sort of optimization. So this is the general idea of LSM tree. LSM tree is used by Cassandra. I think DynamoDB also uses it, and the recent version of MongoDB in WildTiger have support for LSM tree for like really faster writes and good read throughput as well. So yeah, this was all about LSM tree. If you like the video, do let me know in the comment section. If you have any doubt, do let me know. I think it is a bigger topic and a little bit difficult to understand, but try to give it a read on your own, and maybe you will find it like click in your brain and it will be really awesome. So thanks for watching this video, and I'll see you in the next one. Thank you.